This is a lecture on the atomic radius of atoms. We will review its definition, its trends on the periodic table, and the chemistry behind its trends. Atomic radius, one of the many ways to classify atoms, is generally stated as being the total distance from an atom's nucleus to the outermost orbital of electrons. Think of a radius of a circle, with the nucleus at the center and the outer electron shell as the edge. This description is called the van der Waals radius. A second definition of atomic radius is half the distance between the nuclei of two bonded atoms of the same element. This is called covalent radius. Remember, van der Waals and covalent radii are the same thing. They're two different ways to describe the same phenomenon. Van der Waals radius of hydrogen is the same, both quantitatively and qualitatively, as the covalent radius of hydrogen.
A basic review of the atom. The atom is made of three basic parts: the neutron, which is large with no charge, the proton, which is also large with a positive charge, and the electron, which is small with a negative charge. Protons are tightly bonded to the neutrons by strong force in the nucleus. The electrons, however, are free to move outside of the nucleus in quantums, or energy levels. Because of their opposite charges, electrons and protons attract each other, and this is called the intermolecular force. As you will see later in this lecture, this relationship is one of the most important factors that contributes to the size of an atom.
As atomic radius is studied, two major trends arise on the periodic table. Atomic radius increases as you descend the periodic table and as you traverse it from right to left. These trends are clear in a diagram like this, where the largest radius occurs in the bottom left-hand corner of the periodic table. Again, atomic radius increases as you descend the periodic table and as you move right to left across the periodic table. Atomic radius increases as you descend and increases as you move right to left.
For the downward trend of the atomic radius, the radius increases as you descend because you're adding an energy level. Each additional energy level adds a set of valence electrons, which increases the distance between the valence electrons and the nucleus. For example, lithium has a smaller atomic radius than sodium because sodium has more energy levels. Remember, as you descend a column, the radius increases because of the additional levels. In this example, we're only going to demonstrate the valence electrons, so that's why there aren't a lot of orbitals. But protons are shown in red, neutrons are shown in blue, and electrons are green. So as a row is traversed from left to right, the energy level, n, for the row on the periodic table, remains constant. Since this isn't changing, the only significant difference in the elements is the number of protons each one has. In this case, it is safe to assume that the electrons can be ignored. Elements on the right side of the table have more protons, meaning they pull their electrons closer to the nucleus, compressing the distance between them and making the atomic radius smaller. Electrons on the left side of the table have fewer protons, meaning the attractive force on their electrons is less, and the electrons remain farther away from the nucleus, making the atomic radius bigger.
You rock. What's up, man?
What's up, man? How you doing?
How you doing? How you doing on AP Chem 2?
I got another not yet today, man.
Oh,
me
you too? Was that periodic trends objective?
Yeah, man. Bruh, you got to know the periodic trends.
It's a periodic trend. neutrons.